Springs are objects that only exert a force if some displacement appears in the spring. In other words, when the spring is at its natural length or its equilibrium position, then there's no force at all. Likewise, a capacitor is a device that only has a voltage across it if there's some amount of charge stored up on the plates. If the charge is zero, then the voltage is zero. So we see this equation sometimes written in triangular form. It says charge is equal to voltage times capacitance. In this case, the capacitor is a parallel plate capacitor, and we also have an equation that says capacitance is equal to epsilon. If it's an air-filled parallel plate capacitor, then we call it epsilon naught. So it's epsilon naught times A over D, where A is the area of the plates and D is the separation of the plates. Now let's rearrange equation number 1, and it would say capacitance is equal to charge divided by voltage. So which is right? Is capacitance charge over voltage, or is it epsilon naught times A over D? Well, of course, both equations can be true, right? And we often refer to this second equation as the Capacitor-Maker's equation. So think of it like this. As the charge gets greater and greater and greater, as the value of Q increases, then what happens to the amount of capacitance? Does it increase or decrease? Well, if you look at equation number 1, you might get fooled into thinking there's a direct proportionality, that if Q gets greater and greater, C will also get greater and greater. But that simply doesn't make any sense. The capacitance shouldn't depend on how much charge is on the plates. The capacitor should only depend on how much area and what the separation is. So in fact, the only way in which the charge could get greater and greater is if the voltage is also getting greater and greater. And they grow together in direct proportion in order to keep the capacitance constant. Likewise, there are some forces that don't depend on position, but instead are velocity-dependent forces, like the drag forces that act on a falling coffee filter. In that case, F equals BV. There are some devices in an electrical circuit that don't have a voltage by storing charge. Instead, they have a voltage when the charge flows and constitutes a current. We say V equals IR, or just as well, V equals R times I. We can also write that one in triangular form. We know this equation is Ohm's law, V equals IR. And so if we rearrange that, we get R is equal to V over I. But we also know that if the resistance is in the form of a long straight wire, and that wire has a cross-sectional area A and a length of L, then there's another equation we think of that says R equals rho, a quantity known as the resistivity, multiplied by length over area. So which equation is correct? Well, once again, both equations can be correct. And we can say something like this. As the current increases, as the current goes up, what happens to the resistance? Well, that's kind of a silly question. With more and more current, the resistance shouldn't change. The resistance should only depend on the length and the area. And so the only way in which the current could go up is if the voltage is going up in the same fashion. And so the voltage and the current grow together in order to keep the resistance a constant value. Actually, that's a little bit incorrect if you want to get really technical. As current increases, sometimes that causes the wire to get hotter. And with increasing current and higher temperature, then there's a change in the resistivity. But if we consider an idealized case when there's no temperature dependence on resistivity, then of course any change in current should not produce an effect in the amount of resistance. And so this second equation we can refer to as the Resistor-Maker's equation. There are other devices that only have a voltage, not so much if there's a charge or even a flow of charge, They're devices that only have a voltage if there's a rate of change of current. We say that in that case, the voltage is a back voltage, a back EMF, equal to negative the inductance multiplied by the rate of change of current. And this is a lot like saying there are some forces that are not position dependent, like they are in a spring, or even velocity dependent, as they are for the force of air resistance. There are forces that are acceleration dependent, meaning there's only force if there's a rate of change of speed. And so the constant of proportionality is known as the inertia, meaning if we replace the lightweight sports car with a big heavy semi, then you won't get as large of a rate of change of voltage given the same amount of force if the value of m, the inertia, is greater. So we can think of inductance as being a sort of electrical inertia. It's the quantity in an electric circuit that guarantees that the current can't initially start out at zero and then in an instant become non-zero. The current has to grow in some fashion to overcome the electrical inertia. So we can put this equation in triangle form, and we can say that the voltage is equal to the inductance multiplied by the rate of change of current. And here we're just taking magnitude into consideration and ignoring the minus sign. So is there a second equation known as the Inductor-Maker's equation? Well, let's go back to the capacitor-maker's equation and see if we can figure out where this equation came from. After all, this one only applies to parallel plate capacitors. You've probably seen other capacitors before. What if you had a solid metal sphere and then surrounded it by a spherical shell? By definition, that should also be a form of capacitor. After all, it's two different conductors, an inner conductor, an outer conductor, and they're separated by some insulator. We often say the insulator has dielectric properties. Is the equation the same for a spherical capacitor as it is for a parallel plate capacitor? Of course not. We often go back to equation number 1, the very definition of capacitance. Say, I can derive a formula for the capacitance if I take charge and divide it by voltage, where voltage can be found in a number of ways. We could take the integral of E dot ds, but then the question is, how do we get E? We could get E by brute force, or we could get electric field using Gauss's law. And so we took several steps, and I would encourage you to go back and review your previous notes or previous lectures and see how do we go from equation 1 to this equation, and then how do we go from this equation to this equation, and then how would we apply that all over again for the case of a spherical capacitor. Well, we're going to take a similar approach when it comes to inductors. The Inductor-Maker's equation depends on the type of inductor you're interested in. So we can make inductors out of just a single winding of wire. We can make inductors out of a few windings, or we could pack the windings very close together and wrap them on an iron core, and in that case we would have a solenoid or an electromagnet. Another arrangement we can do is take that very solenoid and wrap it around on itself, and in that case make a shape known as a toroid. In all these cases, the inductance should be a function of the geometry, very much like the resistance of a cylindrical wire is a function of the geometry, the length and the area. And the capacitance of a parallel plate capacitor is a function of the geometry, the area and the plate separation. For example, the inductance of a solenoid probably depends on how tightly wound the coils are, how great the cross-sectional area is, and perhaps the overall length of the solenoid. So in a future video lesson, we'll see if we can apply equation number 1 in order to derive a set of Inductor-Maker's equations for various shapes of inductors.